Here is a simple-sounding question with a genuinely shocking answer. You want to build a slide between 2 points, a high starting point on the left and a lower finishing point off to the right. A ball will roll down it under gravity. Your goal is the fastest slide, the shape that gets the ball from start to finish in the least time. So what shape should the slide be? Almost everyone says a straight line. It is the shortest path between the 2 points, so surely it is the quickest. But watch what happens when we race a straight ramp against a certain curved one. They start together, and the curved slide wins, not by a little, by a lot, even though it is a longer path, even though the ball travels farther. The shortest route is not the fastest route. The fastest shape is a special curve, and the search for it became one of the most famous problems in the history of mathematics. So why on earth would a longer path be faster? The secret is speed. On a gentle straight ramp, the ball accelerates slowly the whole way down. It never gets going very fast. But imagine a slide that drops steeply right at the beginning. That early plunge lets the ball pick up a lot of speed almost immediately. And once it is moving fast, it can cover the rest of the distance in a hurry, even the flatter part near the end. So there is a trade-off hiding in this problem. A straight line keeps the distance short but keeps the ball slow. A path that dives down early makes the distance longer, but it buys speed, and speed, it turns out, matters more. The fastest slide is the one that strikes the perfect balance. Drop steeply enough to gain speed fast, but not so steeply that you waste distance going almost straight down. There is exactly one curve that gets this balance perfect. Let's actually run the race, with 3 slides at once. First, the straight ramp, the obvious guess. Second, a slide that plunges almost straight down and then runs flat along the bottom. Surely that early speed boost makes it the winner. And third, our mystery curve, a gentle-looking arc that swoops down and around. Release all 3 balls at the same instant. The straight ramp is slow and steady, falling behind early. The steep plunge does grab speed fast, but it wastes so much distance dropping straight down and loses energy at the sharp corner that it cannot keep up. And the mystery curve glides ahead of both, reaching the finish first every single time. It is neither the shortest path nor the steepest. It is the one that blends falling and traveling into the perfect compromise. That winning shape has a name, the Brachistochrone, from the Greek for shortest time. So what exactly is this perfect curve? Here is the beautiful part. Take a wheel, mark a single point on its rim, and roll it along the ground. Watch the path that one point traces as the wheel turns. It sweeps up and over in a series of arches. That curve is called a cycloid. And astonishingly, if you take one arch of that cycloid and flip it upside down, you get the Brachistochrone, the exact fastest slide. The shape that a rolling wheel draws in the air is the very same shape that carries a ball downhill in the least possible time. There is no obvious reason these 2 things should be connected, and yet they are precisely the same curve. The fastest path between 2 points, the one your intuition swears should be a straight line, is secretly the track of a point on a turning wheel. That is the kind of hidden unity that makes mathematicians fall in love with their subject. This problem has a wonderful history. In 1696, the Swiss mathematician Johann Bernoulli threw down a public challenge to the greatest mathematical minds in Europe. Find the curve of fastest descent. It was a gauntlet, a test of who was truly brilliant. The story goes that Isaac Newton, by then older and busy running the Royal Mint, received the problem one afternoon and stayed up that night until he had solved it, sending in his answer anonymously. But Bernoulli, reading the unsigned solution, instantly knew who had written it. He said he recognized the author the way you recognize a lion by its claw. Bernoulli's own solution was the cleverest of all. He imagined the ball as a beam of light, bending as it sped up through layers of glass because light always travels the path of least time. By turning a falling ball problem into a light problem, he found the cycloid. It was a flash of pure genius. And the cycloid has one more secret, somehow even stranger than the first. Take that same upside-down cycloid and place several balls on it at different heights. One near the top, one halfway up, one near the bottom. Now release them all at the same moment. Common sense says the ball at the top, with the farthest to travel, should arrive last, but it does not. All of the balls reach the bottom at exactly the same instant. The ball that starts higher falls through a steeper section, gains more speed, and races down faster. And it works out perfectly, so that no matter where a ball begins on the curve, it always takes the identical amount of time to reach the bottom. This property is called the tautochrone, meaning same time. It is so precise that the great scientist Christian Huygens tried to use it to build a perfect pendulum clock, one that would keep flawless time no matter how widely it swung. One curve, two miracles. So the next time you see a slide, or a ramp, or a skateboard ramp curving down into a bowl, remember the cycloid hiding inside the question of speed. The fastest way down is not the most direct way down. It is a curve that knows to trade a little extra distance for a lot of early speed. And that same curve, drawn by a rolling wheel, turns out to be the shape that lets a ball forget where it started and always arrive in the same time. What looks like a simple playground question opened a door to some of the deepest ideas in mathematics and physics. The principle that nature, again and again, chooses the path of least time. The straight line is the shortest distance between 2 points, but it was never the fastest. This has been actually rendered, where we show you how things actually work. If this surprised you, you know which button to press.